Welcome back. Today is January the 28th, and we're going to continue here learning and processing NMRs. All right. So NMR stands for nuclear magnetic resonance, and it's the most powerful technique that we have nowadays. Honestly, with nuclear magnetic resonance, we not just discover and identify molecules, we can also scan the brain and other organs. It's really, really cool. And it's all because we've been able to make NMR three-dimensional. In chemistry, we also sort of kind of, well, we use it in two dimensions. But there's one called COSI that COSI NMR is it almost looks like it is three-dimensional. So it gives you the valleys and the mountains. It's so beautiful. And we will now be learning those techniques here. Those techniques are learned in advanced OCHEM. But I will teach you everything that I can for proton and carbon NMR. All right, and the book talks about other types of NMR techniques. All right, so let's. We last time when we met, we solved for the first molecule on the left, and basically what you can do with this numbers here is actually you can actually make propose a spectrum with this. So let me see if I have enough room here to squeeze it. Let's see. Check this out. I'm gonna use a red pen. So imagine that you have a small NMR spectrum here. I'm gonna do kind of small, okay? I'm trying to get that line. There you go. All right. So imagine that this is 0, and here is, let's say 10 in the NMR. You can actually reproduce these NMR. You will have a triplet at 0.9. That one. So it'll be something like, if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 here. So this would be our NMR for this one. And I'm only going to do this one for this one. So you get the idea. So at 0.9, you will have a triplet. Something like that. And this triplet will integrate for 3. So have an integration that is 3 H's. Alright, then you will have a sextet at 1.5. So 1.5, you will have something that looks like has 6 peaks. 1, 2, 3, 4, 5, 6. It'll look like that. And this will integrate for 2 hydrogens. So that will be the second signal here. The third will be at 3.6. So around here, you will have another triplet that will integrate for 2. So it'll be a smaller triplet than the other one that we have. And so this one will integrate for 2 hydrogens. And finally, the D will be a broad singlet anywhere between 2 and 5. So I'm just going to put it right around here. So that will be my broad singlet. And there will be nothing else. There will be a flat line. So this will integrate for 1 hydrogen. Actually, I can show you something really super duper cool that I have in this computer. So I can predict that NMR too. Let me do here on ChemDraw. So remember that. So it had that kind of pattern. The one that is the exchangeable, the OH, could be anywhere between 2 to 5. So it will be here, anywhere in this range. And I was thinking about the question that Lucas asked me last time. Why the hydrogen on the oxygen doesn't have a splitting with this CH2 right here. And I think what isolates the signal is the lone pairs of the oxygen. So if you have a nitrogen, that nitrogen group also has a lone pair, sulfur. Those three will give you isolated signals for the proton attached to the heteroatom. So the electrons are blocking are de-shielding basically that signal. All right, let's see. Yeah, thanks, Lucas. All right, Kaylee, sounds good. All right, there.
Question, Dr. Odin. So the lone pairs are de-shielding. That's why it's isolating it?
Yes.
Okay.
Yeah. It's the only logical explanation that I can give. For something like this, like when you have a carbonyl, yeah, you don't have any neighbors, but it's carbon, so it's different. We're gonna see that an aldehyde, when you have an aldehyde, for example, the aldehyde can, let me see, 1, 2, 3. An aldehyde. No, an aldehyde is also isolated. An aldehyde is also isolated because you have the carbonyl and there's no neighbors next to it. All right, so check this out. Check this out. I'm gonna draw for you this molecule, and I'm gonna predict the proton NMR. So I'll have 1, 2, 3, and then right here is an OH group. So basically we have 1 propanol. All right, and I'm going to request, for that structure, I'm going to predict the proton NMR shift. Look at that, beautiful thing. The same thing that I just did. Notice that you have your triplet, the tall triplet at 0.9. It says here 0.94 with precision. This one will be your sextet at around 1.6. We have that. We have around 1.5, which is fine. And they predicting at 1.59. Then we have another triplet at 3.59. We have 3.6. How cool is that? And then the OH, they put it just like I did, anywhere between 4 or 5. So, but it could be anywhere between 2 and 5. And I didn't actually prepare this. I'm just teaching on my feet right now. Pretty cool, huh? That's exactly the same thing that I predicted. Well, Calvin, if you forgive my scribbles here, yeah, it's exactly the same thing. All right, pretty cool stuff. Right now, you know how to assign the signals, and you can actually draw the structure of not the structure. You can draw the shape of the NMR, how it will look like. You can draw the signals. I have done that in the past. I'll give my students something like this, and I said, predict the signal for this molecule, predict the proton NMR signal for this molecule, and draw a proposed NMR spectrum. And then you do this little thing that I did here. All right. All right. If you have a question, just pop it up. I'm willing to answer right away. All right. So let's go to the number 2 molecule here in the middle. I'm going to use a different color pen so that we keep this consistent. All right, so we have, what do we have here? We have a methyl, methylene. This is a methyl group. Check this out. This is called a methyl, and this is called a methylene group. All right, so you can build up your vocabulary a little bit. And we have a chloro. The chloro is not seen in NMR. All right, actually I should have left that in there. I'm gonna write it down again. Methyl and methylene. So that will be that group, and then this will be this one. And I'm going to label them first. So I'm gonna go from left to right, A and B. So I'm gonna have two signals. So help me out. How do I start here with this? So I have that. What number do I start for that molecule?
0.9.
0.9. Very good. So we start with a 0.9. Let me turn up the volume a little bit so I can hear you better. Let me go back here. So we start at 0.9. Do we have a beta group? So looking now,
Yes.
Yes, right. So I'm looking at this signal, and I have this is an alpha atom, and here's a beta atom. So 0.9 plus 0.3. I'm gonna put a parenthesis beta, and this is going to be equal to 1.2 ppm, represented with the delta sign, comma. What kind of multiplicity will you observe, or splitting? Remember, splitting and multiplicity is the same thing. It's two ways of naming how many peaks you're going to get in a signal.
Would it be a triplet?
Yes, it will be a triplet because the CH3 has two neighbor hydrogens, and 2 plus 1 is 3. So that will be a triplet. Very good. And it integrates for 3 hydrogens. All right. What about signal B? We only have 2 signals here. Signal B will be what? We start with what?
We'll start at 3.0 and then you add 0.3 because it's a methylene.
Excellent. We start at 3.0. Check it out. Because now you have a carbon attached to a chlorine. So don't get fooled with this one. You look for the higher functional group, because now the chlorine is going to have a bigger effect than the carbon that is next to it, right? So you have to pick this one. So you start at 3.0, and just like Ben said, you have to add a 0.3 because it's a CH2 group, and it's not. We don't have a beta group for it because there's only alpha groups to it. All right, so this will be 3.3 ppms, and let's say, what kind of multiplicity do you expect? Go ahead. Hello?
I said quartet.
Quartet, yes. Who was this?
Isa.
Isa, very good. Quartet. And this quartet will integrate to how many hydrogens? That will be the integration.
2.
2. Very good. And that's it. That's it for that one. All right, let's do the one on the right side. I think I still have, on the second page, we have some very interesting signals there. All right, so let me switch pens. Hold on a second, I have something here on my screen. All right, here we go. All right, so I'm gonna label this A, and then B, and then C. Alright, so I have 3 different signals for protons there. The carbonyl is not going to show up here. Alright, but it will in the carbon NMR. So I'm going to start with A. What does A is? Alright, so if you can help me out so we can speed up the process. So I want to see if you understand this. Anybody, any brave soul out there, check out the table. Where do we start with that?
It'll be
0.9.
Yes, it'll be a 0.9. And what else? Do we have
0.3. 0.3 for the beta.
Yeah, we have a beta group 0.9 plus 0.3 because we have a beta group. So this will be going this way in this direction. This is an alpha group to it, and this is a beta. So beta, this carbon is sp2, is different than an sp3 carbon or hydrogen. So we have a beta group, and this is equals to 1.2 ppms. What kind of multiplicity?
Triplet.
Triplet.
And Bear asked how exactly we get to triplet. Could I attempt to explain it?
Yes, please. And who is this, please?
Paige.
Paige, how are you, Paige?
I'm good.
I cannot see. I cannot see who's talking. This is weird. Hold on. Oh, there you go. Now I can see who's talking. All right, Paige, go ahead.
So when you look for the multiplicity, you look at the H's surrounding it, and then you add one more. So the neighbor to A is B, so it's H. The H is on B plus 1. If it's a CH3, if it was directly next to the C double bond O, then you wouldn't have any neighbors necessarily. But because it's got the H2 on that methyl or CH2 group, then it's the neighbors of the H's plus 1.
Excellent.
So
Excellent, Paige. This is excellent. I don't need to add any more to it. And this will be integrated to 3 hydrogens. Now, usually what I do is, you're going to see that when we are going to be we're putting the puzzle together, I'm going to be drawing the signal of interest. I'm going to put it on a square. Now I'm going to erase this, and the next is B. So my signal of interest is going to be B. So I'm going to look at the B signal, and I'm going to check out how many neighbors does it have. So I look to the left now, and I see a CH3. So this will be 3 plus 1. It'll be a quartet. All right. So we know. So we know that. So what kind of signal from the chart? I start here. Anybody? Which one would you pick from this? You have to look for a CH3 attached to a carbonyl.
You go with 2.1.
2.1, exactly right. That's what we're looking for.
Notice then you're going to have to add 0.3 more because it's a CH2 instead of a CH3.
Absolutely right. Let's check it out. So let's do that. Very good. That was my boy Jeffrey Moser, right? I recognize that voice.
Yes, sir.
All right. So I'm going to start with a 2.1 plus a 0.3. I apologize here on my. Don't get confused with this. I just realize it. Another version that I used earlier had that signal at 2.2, so I put 2.2 there. But the paper that I gave you, this book has it as 2.1. So we're gonna stick with what we have. So we're gonna do a 2.1 plus 0.3, which is a CH2 group. All right, and that's gonna be equal to 2.4 ppms. And the CH2 group has only 3 neighbor hydrogens, so 3 plus 1 is 4. We're going to have a quartet, and that signal for B will integrate to 2 hydrogens. Bear, do you get that? All right. I found this video pretty helpful. Okay. I will watch it later. Not yet. Okay, not yet. Not yet. All right. We'll keep on working with you. All right. All right. So let's do signal for C. Well, all right. Sounds good there. All right. C. So what do we have with C? So do we start? What number do we start here with C? That will also be what? Jeff, you got this.
2.1.
2.1. Yes, same signal as the other one. The difference is one was a CH2, the other one was a CH3. And this will be a chart value. I don't have to add anything else to it. And what kind of multiplicity this signal C will have? Anybody?
Would it be a singlet since it doesn't have any hydrogen neighbors before it?
Yes. It will be a singlet. And it will integrate for 3 hydrogens. All right, I think you guys are getting the hang of it. I'm liking it. Let's practice a little bit more. I have 2 really cool examples here. These instructions are the same for both, so we don't want to go over there. First thing we're going to do, again, let me switch pens. I really like the red marker for some reason. A, B, and C, all right, will be those 3 signals there. All right, let's start with A. So what do I have in A? I have notice now these are linear structure. We went from condensed structures now to linear structures. Now that this is a little more advanced, but I think you can do it.
You're going to start at 2.7 and then add 0.3 because it's a methylene and another 0.3 because it has a beta group.
My man, Ben. Excellent. So let's recap all that and we'll explain it. So we'll start with a 2.7 because we have a C next to a bromine. So we're looking at that. 2.7. So 2.7 for initial plus is a CH2, so we had to add 0.3. CH2 plus 0.3 more because we have a beta group. Where is the beta group? Ben?
It's attached, or it's the chlorine attached to the adjacent carbon.
Excellent. Check this out. If you go, this will be his alpha. This will be his beta atom. So you keep on counting. This is to the right of signal A. All right. Very good. And then this is all going to be equals to 3.3 ppms. What kind of splitting patterns we will see? How many hydrogens are in B?
It'll be a doublet.
Yes, it'll be a doublet because there's only one guy right here. If you're unsure, draw it. And it'll integrate, this one integrate for 2 hydrogens. Awesome. Now, this was we were looking at that signal. Now we're going to look at the B signal. So the B signal is this one right here. All right. What do we have in B?
Doesn't, oh no, you're talking about 1, aren't you? You haven't got 2 yet.
Can you repeat?
Are you talking about B being a doublet? You're talking about A, right?
A is a doublet. Mm-hmm.
Right. Okay.
Yeah,
All
yeah.
right. Sorry. Thank you.
No, that's okay. Now we're going to look at B. That's the signal that we're interested in. That's CH right there. All right, B. what do we start with B? So what that carbon is attached to?
We start with 3.
Yes, we start with a 3. It's a carbon attached to a chlorine. But it's not a CH3. So we have
And
to...
then we add 0.7 because it's a CH.
Let's see. Yes, definitely. Oh, that must be Anita Baluch, right?
Yes.
I recognize that voice. Very good. Absolutely, yes. So here we go. So we start with a 3.0 plus a 0.7 because it's a CH. How cool is that? We have a new example here.
Do we also add another 0.3 for the beta group with the...
Absolutely, Skylar. So where is the beta group for that signal?
It's the bromine.
It's the bromine. Exactly right. So we're going to look to the left now. We're going to look to the left. And we're going to see that we have a beta group. This will be alpha to it. And then this will be its beta group. We have a beta atom. Excellent. So that is going to give us what? 4.0. 4.0 ppms. What is the multiplicity for that signal? How many neighbors hydrogens does B have?
Would it be a sextet?
It will be a sextet because it has 5 neighbors. And that is Aaron, right?
Yes, sir.
Excellent. Sextet. Were you able to finish the lab, Aaron, last time?
Oh, yes, sir. I got it done.
Awesome. The integration for that signal is how many hydrogens?
2.
1.
1?
1.
Is it 1?
Mm-hmm. Yes, it's 1. Because there's only one there. One little guy there. All right. Let's do the signal C. So what do we start with?
Dr. Odin,
Yes.
I do have a question about the beta.
Yes.
Are you going to have that every single time? Like, is there always going to be a beta?
Not necessarily.
Okay.
It depends on the, for example, for this case, A and C have beta groups. Let me see. All of them have. A, B, and C. All of them have beta groups to it. Okay.
How does C have the beta group? Just because of the CH neighbor?
No, check this out. For the beta group, what you need to do is to count to the left or to the right until you find an atom different than hydrogen or carbon, a carbon that is sp3.
Okay.
So for C, check this out. This is his beta. That, and then this, I'm sorry, that's his alpha. This will be his beta.
Okay.
You see it now?
Yeah, so the alpha can be the CH group.
Yeah.
And then the beta has to be a different one.
Exactly. Beta have to be a different one. So that's
Okay.
what with the direction, I showing the direction with the arrow. Sometimes we go to the left, sometimes we go to the right. So for C, why is it doing this? Okay, give me a sec. For C, it keeps on doing that. I'm not saying to do that. Hold on, let me scratch somewhere. Hold on a second. It's not giving me points. Alright, I'm gonna switch and switch. That will help. This computer, right now I'm really stuck. Alright. I'm gonna slow down because I am totally OCD and this program wants to restart. Alright, I'm gonna take it easy. It's good for my heart. Keep on doing it. Alright, I gotta laugh it out. If not, like I'm gonna lose it. I don't want to in front of all my students. Now I'm pretty sure I'm not losing my cool because of this. The worst comes to worst, I'll save it. How about that? I'm gonna save this. I don't want to lose it. We'll throw a commercial and then we'll reset and we'll restart. But okay, let's see. If I cannot draw, I'm gonna close it and reopen it because I hit a patch or something. It's not letting me draw. I learned with years of teaching that it doesn't matter how much I get worked up. If the computer doesn't respond, there's nothing I can do about it, especially teaching online stuff. See? And I think it's all due to Zoom. Zoom really sucks up all the memory and speed of the computers. All right, this is not responding. Can you guys hear me?
Yeah.
All right, so at least we're connected. See this? I'm gonna close this program because it's not working. All right, just be patient. I'm sorry. All right, so I'm gonna open that up again. See, there's no need to get worked up. No need for that.
You need to be a mental coach.
Exactly, right? Hey, I
No
have.
need to get worked up.
I know. I have seen professors losing it. They even slam the computers when. Yeah, I've seen it. And I'm like, it's funny to me. I just laugh about that stuff. Like, come on, you're gonna
You
kill.
need to play more games and just sit over there beside the dugout and then just be like, oh yeah, just calm it down.
Exactly. There's nothing I can do right now. So I'm trying to open this file. Maybe it's too big because I keep on adding stuff to it. But yeah, you'll be a great coach, Kaylee. I think you don't lose it either.
I hope so.
Yeah. All right. So I'm trying to opening this. Probably opened 3 times now. That's why I prefer in-person classes. All right, it's gonna open. I'm sorry. I mean, this computer might be getting old. I keep on thinking it's new, but this thing is getting 3 years old now.
Don't worry, you're still better than 99% of my other online professors.
Yeah, have you seen them? Have you seen them losing it, getting frustrated?
Oh yeah, big time.
Yeah, I mean, I don't know why they do that. I mean, it's like, come on. I mean, there's nothing we can do about this thing.
We had 60 people on a Google Doc the other day. It was not good.
That is hilarious. I'll be laughing if I see my professor getting frustrated because of a computer. Here we go. We're back almost, and it's very slow, but I think it's because of Zoom. Zoom has that. Let me close this. I'll need that. I'm so sorry, guys. I'll try to do my best to make it up here with time. 33. That's I gotta get to 39. So I'm right here. Yep. In about a minute, we'll be back. There it is. Okay. Thank you. See, and my heart is still healthy because I didn't get angry. All right. All right. C. Okay. I'm trying to do red, but this is interesting. All right. Okay. He wants to do it in green. Let's do it in green. All right. So for C, what is the start signal for that? You have a carbon attached to a carbon, so we need to start with a 0.9. Alright, so I'm going to try to switch it one more time.
And then you got that beta, so that would be the 0.3, right?
Yeah. So we have 0.9 plus 0.3 because we have a beta group. And this is equal to 0.2 EMs. Kaylee, what would be this multiplicity for this signal? How it would look like?
So I'm not good at this, but
we're looking at this.
Is it okay? Is it just the singlet?
Well, you have one neighbor, so it's 1 plus 1.
So it's a doublet.
It's a doublet, yes.
Okay.
So C, only C is one neighbor.
Okay.
And that's B. And so it'll be a doublet.
So you just add it by 1.
This plus 1. One neighbor plus 1. All right. And the integration is different, though. The integration will be
3
hydrogens. Very good. All right. Let's do the one on the right side. The one on the right side, it's more interesting. All right. Check this out. I'm going to do A, B, and C, because the B will be all aromatics. Notice that we have a pattern here. What will be this pattern? What kind of molecule is this? Is it ortho, meta, or para? Remember that?
Is that a para?
It's para because, yeah, it has a 1,4 substitution. All right, so you have substituents on 1 and on carbon 4. All right, very good. It's para. So para, it's interesting because para, we're going to learn that para will give you 2 doublets that are like this. And they will both integrate for 2 hydrogens. Don't draw this. I'll show you that later. All right, and that's because this CH and this CH are equivalent, and this CH and this CH are equivalent. So both of them only have one neighbor. So this signal will see one neighbor on the right, so it's plus 1. That will be a doublet. And then this signal sees one neighbor on the left, so plus 1, that will be another doublet. And because it's a double up signal, you have an integration of 2 for both. All right, we're going to learn this in the next few slides. All right, so let's do this one out. So we have A. So what does A start with here?
It starts with 3.
Starts with 3.
2 alpha groups. It's 2.3 minus 0.9, and then it's a methylene, so you add another 0.3.
Excellent. So so let's do it like this. So I'm gonna do a little different order, but you got it right then. So it's 3.0 because it's a carbon attached to a chlorine. It's this one again. And it's CH2 group. So I have to add 2, 0.3. It has a CH2 group. Then this one has the capacity for 2 sharp values. So if you notice that, so also you have a carbon attached to a phenyl ring, and so that is, we're dealing with this premise here. So if you have if there's a second option of a group that you can name, then you have to add the second value and subtract 0.9. All right. So what I'm saying is that signal could also be this 2.3. You see that? So you have this one, the carbon close to the chlorine, and you have the carbon attached to the phenyl. All right. So awesome. So let's go back over here. And so then you have to add 2.3 minus 0.9. How much is all that? that is equals to 4.7. And what kind of signal?
Quick question, Dr. Oda.
Yes.
Sorry. You do that 2.3 minus 0.9 because the carbon has 2 alpha groups attached to it, right?
Yes, we have 2 alpha groups, and you could have had this alpha group here, and the 3.0 here, and it's the same thing because you're adding. It's an addition. Addition and subtraction is what's the word for that?
The property of addition or whatever that.
Yeah, like community or something. I forgot the term that the mathematicians use. Yeah, you know what? Huh? Commutative? Is that what it is? I think so.
Yeah, I'm pretty sure.
Yeah, I think so. So it doesn't matter the order of the addition doesn't change the final result. All right, so doesn't alter the final result. All right, so that will be 4.7. We have a singlet, right? That signal will be isolated. A has no H's, neighbors, and it'll integrate. How super duper cool is that? All right, let's do B. So what is B? It signals in
Hey, Doctor.
a chart. Yes, ma'am. Go for it.
So whenever you add the 2.3 for the phenol group,
Yes.
because it's the phenol to the CH3, do we not add another 0.3 because it's CH2 over there?
No, we're taking care of that with the minus 0.9. We already.
Okay.
We only added once. We only added once.
Okay. And then the beta group too, there isn't one for A.
Let's see if there's a beta group for. There's no beta group for A. There's no beta group for A. There's alpha groups. There's two alphas. There's 2 alpha groups. You have the chlorine to the left, and also the CH2 carbon to the right. Both are alpha. All right.
Thank you so much.
You're welcome. All right. So what is the signal for the benzene ring hydrogens on the chart? Anybody found it? It's 1 7 to 8. Very good. It's one that you have to get used to it. We'll see it a lot. So that'll be 7 to 8 ppm. I say chart. We're not gonna touch it. And at this point, you don't know that you will have two set of doublets. So let's just call it multiplet for now. Oh boy, I have like very little memory. That will integrate. How many hydrogens can you count on that ring? Four. Very good. All right, let's do the signal for C. Okay, who can help me out? What will be the signal for that? Based on this thing.
Would be 2.3.
2.3. Very good. And that will be a chart value. So 2.3 ppm. And what multiplicity would you expect? Does this have any neighbors, these hydrogens here?
No, so it'd be singlet.
Singlet, and it will integrate for 3 hydrogens. Very good. Okie dokie. Any questions up to this point? All right. Let's reproduce the proton NMR for that molecule. Let's see. All right. So if I take this, and I go fix this. I'm gonna take. I'll do that. ChemDraw needs to be used with a mouse because it gets really bad trying to do it with the fingers or the little pad here. Alright, so we have that. Check this out. We'll predict the proton NMR. Alright, and notice that so here you have a singlet that integrates for 3 will be this guy. We said 2.3, they say 2.919. Here are the signals for the benzene ring, and it's 2 doublets because it's a para group. And then you have this signal here at 4.64, and we predicted that it was 4.7. That's pretty darn close. All right, not bad. This can also predict carbon NMR. We haven't gone to that, but I can predict the carbon. And all you're gonna see is the different types of carbons. So we'll have 1, 2, 3, 4, 5, 6 different carbons. Yes. So we have 1 here, 2, 3, 4, 5, 6. We have a mirror image in the middle of the benzene ring, so we don't count the ones below. Awesome. All right. Let me close this for now. No, I'm gonna cancel that. Let me go back. I'm gonna keep it on. All right. Okay. All right. So I'm gonna switch now to. The completed version of my slides to gain some time here. So we're here, and so we're gonna go to the next slide. We know about integration, so integration now tells us the number of hydrogens in each signal. So notice that the hydrogen in blue will be 3, it will be 1 singlet, and the hydrogens in red will be also a singlet, but they will integrate for 9 because we have 9 hydrogens on the red signal and 3 hydrogens on the blue signal. So we have a 3 to 9 integration, which will be equals to 1 to 3 ratio. All right, I want to talk about this. This is the spin coupling. And Bear, are you there? Okay. Yes, you are. I think I saw a little signal here for the chat. Okay. Okay. So Bear, check this out. I'm gonna explain to you how we get the doublets, the triplets, and the quartets. All right. So maybe, yeah, I'm gonna go ahead and do this for you guys, and then next week, what I want to do next week is to start actually interpreting NMRs. All right, we're gonna interpret that. That's what I want to do. So all this theory is good. We have to do it. All right, so let's do this one right here. Okay, so this is how the chemists figure out how to use the NMR, and we save the physicist from dumping this wonderful instrument into the dumpsters. All right. Okay. So here's A, HA, hydrogen A, we have hydrogen that has one neighbor X. And so the hydrogen A by itself will have one spin. So this is without HX present, right? So that one atom, this atom of hydrogen, label A, has one spin, and it's up. Then, in the presence of HX, it has to change because they both cannot be in the same orientation. So the presence of HX makes the proton HA to switch its spin. The spin will be up sometimes, or the spin could be down, because now it's affecting it. All right. So I put a little mark here, like if it was a tree, and now you have a 1-to-1 ratio. And so a 1-to-1 ratio will give you a nice doublet. How cool is that? Let me move that a little bit to the... I was trying to erase it, but it's not erasing. All right, so I stuck. All right. How about, so that was looking at this signal. So now let's look at HA again. HA now has two neighbors X. All right. So HA will have one spin. This is without the presence of HX. So by itself, it's an atom. It has one spin. All right. So now this HA has now two HXs that can affect it. And so when it interacts with this and interacts with this one, HA can take the following orientation. So it could be both up. So now actually sorry, this is HX. Now HX could be up or could be make it down. Yeah, never mind. I got it. And so so it could be both up or both down here, or in the middle it could be one up and one down. Likewise, this one could be one down or one up at different times. So in other words, you have a ratio of 1 to 2 to 1 ratio. And that's why this creates a triplet that looks like that. So the presence of HX to HA will be 2 plus 1, then it's 3, so it will be a triplet.
Okay, how is it a 1? Sorry.
No, that's
how
fine.
is it a 1 to 2 to 1 ratio?
Yeah, because the possibilities here are 2. Here you have one possibility, here you have 2 possibilities, and here you have 1. You see?
Okay, so on a test, if you give us this, we need to write those 2 in the middle?
Yeah. Mm-hmm.
Okay.
Yes.
I thought that was just a possibility of how you could write them or how they could sit.
And yeah, and this is all mathematic. It's all possibilities based on mathematic possibilities.
All right, thank you.
You're welcome. Well, so let's do this one now. Now it's HA here, and it's going to interact with 3 different HXs. So the first signal you're going to put here is HA without HX. And so check this out. So the first thing is here. Without any of them, it'll be up. Now, when it interacts with the other ones, the other 3, so all these will be HXs. HXs will behave different. They're going to say, okay, all three could be up, and all three could be down. But in the middle, we could be 2 up and 1 down, or 2 down and 1 up, and 1 up. Likewise, this one could be up, down, up, or down, up, up. You see that? And then these two that are down, down, up, they can also be down, up, down, or up, down, down. So what is your ratio here now?
1 to 3 to 3 to 1.
Excellent. 1 to 3 to 3 to 1 is the new ratio. And that's why you get a quartet. Because it'll look like one like this, 2 tall ones, and 1 little one. This will be a quartet. That's why you get those splittings. How super duper cool is that? Alright, so question here. Maybe I have another question here. Alright, let's go to the next slide. Alright, so this summarizes what we've been learning about splitting. So on the left side you have the protons in green. On the right side you have the protons in red. Alright, so the HX in green has one neighbor in red, so it will split into 1 plus 1 equals to 2. Likewise, the red proton HY has one neighbor HX, so 1 plus 1 is 2, so it will split into doublets. So let's do the next one. So in the next one we have 2 HXs and 1 HY, so the 2 HXs will be a doublet because both of them have one neighbor red. So 1 plus 1 is 2, and the integration will be 2 hydrogens. And the signal for the red HY would be a triplet because it has 2 neighbors HX in green to the left. So 2 plus 1 is 3. The next one, both of them have 2 neighbors, so it's 2 plus 1 is 3. The next signal, this one, we're here. Now we'll see that all the green hydrogens have one neighbor, so 1 plus 1 is 2. That will be a doublet that will integrate for 3 hydrogens. And the signal for the HY in red will be a quartet because it has 3 neighbors, and 3 plus 1 is 4, so you have a quartet. The next one, you have 3 to 2 ratio, so the green ones will have 2 neighbors, so 2 plus 1 is 3, it's a triplet, and the red ones have 3 green neighbors, so 3 plus 1 is 4, so that's why you have a quartet right there. And this one is really cool. Notice that the green protons are 6, and they all have one neighbor. So there will be 1 plus 1 is 2, so you have a doublet here. But that doublet, it will integrate for 6 hydrogens. Whether the signal for the HY in red will be a septet, because it has 6 neighbors. 6 plus 1 is 7. So you have 1, 2, 3, 4, 5, 6, 7 signals, and this will integrate for 1 hydrogen. Finally, the green protons, HXs, don't have any neighbors, hydrogen, so all 3 of them will show up as a singlet. All right. Any questions up to this point? All right. Let's go over here. I like to teach this thing. This is what I call the aromatic coupling. Yeah, I have 8 minutes. I think I'm gonna take my 8 minutes to explain that, and then next week we're going to be doing examples from the packets that I gave you. I'm gonna do the package example for that. All right. So check this out. So you have a benzene ring, right? When you have a benzene ring, and you plug one hydrogen, if you see a multiplicity that integrates for 5 hydrogens, that means this is mono-substituted. All right. So what we're seeing here is this. So say for example you have the benzene ring and you have a group attached to it. Let's just call it X. So what you're expecting is that this signal, this H, will be a doublet, because this guy, this H, has one neighbor next to it. So 1 plus 1 is 2. So what would be the signal for this H here? It will be a triplet, because this CH has 2 neighbors attached to it, next to it. So 2 plus 1 is 3. What would be the signal for this guy right here?
It'll be a triplet also.
Also a triplet. Very good, because it has 1 and 2 neighbors right there next to it. All right, and you can go around here. So this one right here will be equivalent to that, and this one here will be equivalent to this. So basically, you expect to have a doublet, a tall triplet that integrates for 2, and a little triplet that integrates for 1. This guy right here, that will be your little triplet, because this molecule has symmetry. You can cut this in half, and you will see that the ones on the top left and top right are equivalent, and the one on the bottom left and bottom right are equivalent. So because you have only one group, X, all of those signals will cram together, and that's why you get this kind of pattern, like a multiplet. And all you can say, okay, right here on this signal, I have 5 hydrogens on the benzene ring. Make sense? Now let's pretend something. Best case scenario, we're going to do ortho, meta, and para. All right. So we're going to have an X group and a Y group. All right. Check this out. So over here, you will have, for ortho, you have an X here and a Y here. For meta is the next one. You have an X there and a Y there. And then for para, this is meta, and para will be an X with a Y here at the 1/4 position. Alright, so I'm going to make this easier for you. I'm going to put all the hydrogens here so you can see them. Got 4 minutes. Let's dissect these signals together. Alright, I'm going to switch pens. I'll look for like a purple, something different. Alright, check this out. Now let's label this A, B, C, and D, because they are all different, right? If X is different than Y, let's pretend that X is an electron withdrawing group and Y is an electron donating group. Check this out. Electron withdrawing groups will pull to the left of the spectrum, of the NMR spectrum. Electron donating groups will push upfield. How cool is that? If I give you that piece of information, you should be able to figure these things out. All right. So what will be the multiplicities for this one? For A, HA, here. Tell me, what will be the pattern here?
Doublet.
A doublet. And this one?
Triplet.
Triplet. This one? Triplet.
Triplet.
And this one? A doublet. So for your ortho, your multiplicity on the benzene ring should be doublet, doublet, triple, triple. And they are all equivalent in height. Double, double, triple, triple. Make sense? All right. How about for, and that's what we see here. Check this out. That's what we see here. So we're expecting, this is kind of hard because this got kind of cramped together. Here is a double. You see that it has two little peaks, and this is a triple that is leaning. So there's a double here and there's a triple here, and you're expecting to have a double and a triple crammed there. That's why it looks like a multiplet. All right. Now let's go do the meta before you get wondering. The meta is one of the coolest to identify, because the meta has this H here. What H is that? I'm going to call it A.
Is that a singlet?
It's a singlet, yes. That is a singlet. How about this one? Doublet. This one? Triplet.
Triplet.
So this will be A, B, C, and D. They will be all different. And this one will be also a doublet. Right? Because they only have one neighbor each. All right. So this one has one of the coolest orientations, because doublet, doublet, triplet. All right. Let's put that here on the spectrum. Here's my singlet. You see that? It's a single. Which doublet is this one? It's the only one that I can see that is clear. Would it be the one next to the X group or one next to the Y group?
It's the one closest to the X.
And that's correct. And why is that?
Because it's an electron withdrawing group, so it's going to pull it down.
It's pulling it down. Excellent, Ben. So this will be D. And right here, crammed together, you have a triplet. This will be C, and B will be here together in that signal. All right. If you give me 1 minute, I can finish the para, and then we can wrap it up. Our para is the easiest one to spot. Every time you see this pattern, a doublet and a doublet, this will be this. So A, so this will be A, and this will be A, this will be B. So A will be on the left, B will be on the right, because the A's are closer to the electron, which will drag it to the left, and the B's will be closer to the Y, so it will drag it to the right. So this is your para will be doublets of doublets, two doublets, and they will integrate for 2. Stop right there. Any questions up to this point? All right, we're also going to learn from this. We're also going to expand this into the W coupling the next time that we meet. Have a wonderful weekend, guys. I'm going to start, see if I can get to online homework. But basically, I don't want to overwhelm you right now. Just hold on for that. But I really want you to like start doing the packets that I have on Canvas for Proton NMR now. Let me turn off the recording. Have a wonderful day.